Hi, welcome to videos on control systems. Today we'll see the transfer function of few electrical circuits. So before we start, let us see these initial slides. Of course, you need to know what is how do we find voltage across and current through resistors, inductors, and capacitors, and we should be knowing what is Ohm's law, KVL, KCL. And since it is control system, we are supposed to know what is transfer function and what are these poles and zeros. What you need to do is you should have a notebook, few color pens, and make sure that you are switching off all distractions. Of course, you need to set aside minimum at least 1 hour to understand this contents of the video thoroughly. Okay, now we will start. So let me start with. Okay, we are supposed, of course, we are starting with a very simple electrical network. So I'm supposed to find what is the transfer function of this. So we know the transfer function of this particular circuit is given by the Laplace of output by Laplace of input. So I want to get this ratio. To do that, let me replace this circuit by its Laplace transform. So I will be replacing this capacitor by its Laplace transform by something like this. So now all these voltages and currents which are V in of t and V naught of t will be now represented as V in of S, and this is R1, and this capacitor will be now replaced by 1 over SC, and this is V naught of S, this is IFS, and this is ground. So now I want to find out what is V naught of S, which happens to be the voltage drop across this capacitor, so which is nothing but IFS multiplied by the impedance of this in Laplace transform is 1 over SC. So let me find what is IFS, which is current flowing through this resistor R1, so which is nothing but the potential difference across this, which is V in of S, V in of S minus V naught of S divided by R1 is my IFS. So let me substitute this IFS onto this equation so that I can write V naught of S is equal to V in of S minus V naught of S divided by R1 into 1 over SC. So upon simplifying, I can just cross multiply this. So V naught of S into S R1C is equal to V in of S minus V naught of S. I can rearrange this. So V naught of S is equal to 1 plus S R1C is equal to V in of S. So ultimately I can write V naught of S by V in of S is nothing but 1 over 1 plus S R1C. This is the transfer function of this circuit, so which is a very simple one. So now this is in time constant form. So now we know that time constant form can be written as something like, okay, k dash 1 plus S tau p. So what is the time constant tau p now? So tau p is equal to actually R1C. So now we know that I can able to represent this transfer function in the S-plane, that is pole zero form. So I have a pole at minus 1 over tau p in S-plane. So now where is the pole? There is a pole at minus 1 over R1C. So I can represent that over here in the S-plane having the real part on x-axis, and it is j omega on the axis. Now I can see if this is minus of 1 over R1C. So there is a pole on the real axis of this S-plane, which is depending on the value of R1 at C. Suppose if R1 is equal to 1 kilo ohm, if C is equal to 1 microfarad, then tau P happens to be this into this, which is 1 millisecond. So then my pole happens to be at, okay, it is minus 1 over 1 millisecond, which is nothing but, so now it will be at minus 1000. So I have a pole at minus 1000. So this will be minus 1000. I'm going to have a pole at minus 1000. So if this is 1 kilo ohm and if this is 1 microfarad, it will going to possess a pole at minus 1000, minus 1000. Fine. So now let us improvise this circuit by having a resistor in parallel to that capacitor. So this is the circuit what you had. This is the circuit what you had. So what I'll do is I'll just rewrite the circuit again. I will write this is again R1. I'll have this capacitor C, but I'll put a resistor maybe in series with this. So this is R2, this is V naught of T, this is I of T, this is V in of T. So this is my circuit. So let me write its Laplace equivalent. So upon writing its Laplace equivalent, I can write. So what I can do now is, so I can write. So this is now plus minus V in of S. This happens to be again R1, whereas this happens to be 1 over SC. This is now R2. This is V naught of S. This is IFS. This is IFS. This is the Laplace equivalent. You can see this has become. Now we are trying to represent this in Laplace form. I am writing the reactance offered by this capacitor as 1 over SC. So now, what is V naught of S? V naught of S now is equal to IFS multiplied by the resistance of this, the entire impedance of this. So impedance, since these two are in series, I can write 1 over SC plus R2 is the voltage drop. But what is IFS? IFS, I can write it as, it is V in of S minus V naught of S divided by R1. So this is the current expression I1. So now I can write, so I can substitute this IFS here and I can write it as V naught of S is equal to V in of S minus V naught of S divided by R1, and this is since I take this as LC, okay, SC as I can write it as SR2C. For taking LCM, I can write this as so and so. So now, what is V naught of S? So I will write this as SR1C is equal to V in of S minus V naught of S into 1 plus S R2C. So now what will happen to this? This will become V naught of S. Let us slightly rearrange that. So it will become S R1C plus 1 plus S R2C is equal to V in of S 1 plus S R2C. Correct? So now I can further rewrite this V naught of S divided by V in of S as equal to 1 plus S R2C divided by 1 plus. So since S is common here, I can write R1 plus R2 into C. Is that fine? This is how my circuit is. Sorry, the transfer function is. Now again you can see this is in the time constant form. The time constant form that what I am looking at now is, So what is that I'm looking at now is, so this is of the form 1 plus s tau z 1 plus s tau p. So tau matlab time constant. So what is tau z? It's, as per this, it is r2 into c. What is tau p? It is r1 plus r2 into c. It's actually time constant. We know the time constant is r into c. Can you see this is r? The r value is now r1 plus r2 and c is as it is. And this is r2c. R2c. Now what we do is we will simply uh, assume the resistance value as, so in the previous case we have considered this as the value of resistance. Now this was 1k, this was 1 microfarad. It has resulted in a pole at minus 1000. Can you see this pole was there at minus 1000, minus 1000 for this circuit, for this circuit. The moment I add, if I add one more resistor 1k here, if I add a resistor of 1k along with the existing 1k and 1 microfarad, what happened to this? It will result in this transfer function. What is the resultant of this transfer function? So if I take this also as 1k, can you see now this is becoming 1k into 1 micro is now 1 milli. And how much is this? This is actually 1k plus 1k is 2k. 2k plus 1 micro is 2 milli. 2 milli. So this is 1 millisecond and 2 millisecond. So what is the cutoff frequencies? So cutoff frequencies are, because now we are looking at the pole position, 0 position. So where is the pole? There is a pole at minus 1 over tau p and there is a 0 at minus 1 over tau z. So where is the poles and zeros for these values of R1, R2 and C? So now as per this, in this S plane, if you add a resistor 1k to this particular circuit which is there in series with this capacitor, I will end up with a 0 at minus 1000. This is a 0 at minus 1000. How about the pole? Pole is at 1 over 2 milli is actually minus 500. See now? So this is the 0 position. The pole has now moved to minus 500. If you compare this and the previous graph, this graph, see now, to this circuit, okay, to the circuit as it is, the pole is at minus 1000. Suppose if you add a pole, if you add a resistor of R is equal to 1 kilo ohm here, so what will happen to this pole position? This pole position which was there at minus 1000 will come to minus 500. Will come to minus 500. So where is 0? There is no finite 0. So actually 0 is at infinity. Now the moment you add this resistor R2 in series capacitor, there is a 0 coming at minus 1000. There is a 0 coming at minus 1000. If you add this, so that's what is shown in this transfer function. You can see this is the indication of 0 coming to a position which is equal to minus 1 over R2C. This is minus 1 over R2C. Of course, the position of poles and zeros depends on the values of R1, R2. And at any point of time, this tau P is always greater than tau Z. This tau P, because you can see it's R1 plus R2 and this is R2 only. Of course, C is common. So naturally, this is, what does this say is, the pole frequency will be always lesser than the zero frequency in terms of magnitude. You cannot have this 0 coming before this, because the time constant of your pole is always greater than the time constant of the 0. So the 0 is always far away from the imaginary axis, whatever the value of R1, R2 is. So it can never come here. What I mean to say is, suppose if you take, maybe let me just take it as, let me take the extreme values. So what I do is, let me take a value of resistors which corresponds to something like this. So let me take this. This is 1K. This let us assume it as 100 kilo. This is maybe 1 microfarad. So, and let us take one more circuit where this is 100 ohm, and this is maybe 10 kilo. So now this is plus minus. Where is the pole? Pole is at minus 1 over R1 plus R2, that is 101K into 1 micro. So what is that? 110 into 1 micro would be, so that will be 1 milli, and let me just tell you the value. So this is, sorry, so now this value is 101x into 1, okay. This is 101K. So this happens to be at minus 101K. 1K radian per second. This is actually frequency. This is in second. This is actually in radian per second. It's in radian per second. Now, what is the zero position? Zero position depends on, we know that this expression is minus 1 over R1 plus R2 into C. This is R1, this is R2, this is C. How about 0? This is actually minus 1 over C R2. So this happens to be at where? So this is at, so sorry, this is not 101. Let me just write this. It is 101 inverse into 1 exponential 3. It's actually at 9.9. This is 9.9 radian per second, because minus 9.9. How much? How about this? This is at 100 inverse into this is 2000. So this happens to be 10, minus 10 radian per second. So you can see this is 9.9 minus 9.9. This is 10. So what you have now is, so the zero is at, sorry, the 0 is at minus 10, whereas this is at minus 9.9. Minus 9. You can see this is always away from this. So even though it is bit away, it is away from that. And coming to this, this is 1 micro. Here is pole. Pole is at minus 1 over 10.0, sorry, 10.1K into 1 micro. So which is nothing but 10.1 inverse into 1000 happens to be 99.00. Where is 0? 0 is at, so now 0 is at 1 into 10 exponential minus 3 inverse is 100. Correct? So now here also, where is this? So this is minus. So pole is at minus 99, whereas 0 is at minus 100. If you take another example where it is something like this, let us take this as 10K. Let us take this as 100 ohm. This is 1 micro. Where is pole? Pole is at minus 1 over, this is 100. So is it not 10.1K multiplied by 1 micro, which is nothing but 10.1 exponential of minus 3 inverse of that is minus 99. Where is 0? 0 is at 1 over minus 1 over 1 micro into 100. It is 1 exponential minus 6 into 100 whole inverse is at minus 10,000. So where is this is minus 99, whereas this is at minus 10,000. Sorry, this is SE. See, now in all these cases, whatever the values of R and C you take, you can never make 0 to come before that. So it's always 0 is having larger negative cutoff frequency compared to the pole. So pole is here, 0 is here, pole is closer to imagined axis, whereas 0 is far away. Here 0 is to too far away from the pole. So using whatever combination of the resistance, you can never make 0 frequency lesser than the pole frequency in terms of magnitude in this type of circuit, because the time constant of your pole is more compared to the time constant of 0. Fine. So what we have done is, so we have considered the first circuit, we have considered this circuit, and we added a resistor in series with this. So what we'll do, we'll add a resistor in parallel to capacitor, try to find what is the response of the responsive circuit. So we'll do that. How do we do? We'll just repeat this. So I will, so this is my capacitor. I will add a capacitor in parallel to this. So this is R1, C, R2. This is V0 of t. This is Vin of t. This is I of t. Let me just take it as a single component. So that will make my life easy. So we'll consider it as a single one. So this is I of t. I'll replace it by its equivalent. So Laplace equivalent. So can I replace this as Vin of s? This is I of s, and I'm considering this as 1 over SC, and this is R2, this is V0 of s. Correct? This is R1. So then what is now V0 of s? V0 of s is nothing but voltage drop across this entire impedance. So it is nothing but I of s multiplied by 1 over SC in parallel with R2. So we have to actually find out the parallel combination of that, which is nothing but, so 1 over SC in parallel with R2 is equal to 1 over SC into R2 by 1 over SC plus R2. So let me simplify this. It is R2 by SC. Upon taking LCM, this will become 1 plus S R2C, and this is SC. This will go with this. So this will become R2 by 1 plus S R2C. So now this, whatever parallel combination you have, now this will now become IFS into R2 divided by 1 plus S R2C. So this is my V0 of expression. So what is IFS? Because I want to replace this IFS. So IFS is nothing but voltage across current through this resistor. I can write V of S minus V0 of S by R. Correct? So I'll substitute it here. So then this will become V of S minus V0 of S into R2 divided by R1 into 1 plus S R2C. 1 plus S R2C. Correct? So this I can further simplify this as V0 of S into R1 into 1 plus S R2C, and I can take this also, and I can take it as plus R2 is equal to V of S into R2. Correct? So that will be your expression. So then can we write this as V0 of S by V of S is equal to R2 divided by what we have, So we have this as R1 plus S, R1 R2 C plus R2. This is what I have. So upon simplifying, so I can rearrange this and write it as R2. I will take this R1 plus R2 like this, R1 plus R2 plus S R1 R2C, S R1 R2C. So I will further rewrite this as, I will just rewrite this as what. So I will rewrite this V naught of S by V naught of S is equal to R2 by R1 plus R2. I will take this R1 plus R2 outside, then this will become 1 plus S into R1 plus R2 into C divided by R1 plus R2. Correct? So now what is finally V naught of S by V naught of S? V naught of S by V naught of S is equal to R2 by R1 plus R2 is your constant term, and then you have 1 over 1 plus S. So can you see, is this R1 R2 by R1 plus R2 is R1 parallel R2? This is actually parallel combination of R1 R2 and C. So this is my transfer function. So my transfer function is this. So the moment you put a resistor in parallel with this capacitor, what happened to the transfer function? So let me just take the first transfer function. The first transfer function without the resistor across the capacitor was given by this. So let me write that also here. See now, without that resistor it was 1 over 1 plus S R1C. Correct? This was the site transfer function when you had R1C. When you have this R1, the difference is, for this circuit you had this other transfer function. For this circuit, when you added a resistor in parallel to capacitor, the transfer function has become this. If you carefully notice, this was actually 1. This was actually 1. That 1 is now replaced by R2 by R1 plus R2. And this tau p, the tau p is now, what was tau p here? The tau p was R1C. But what is tau p here? Tau p is actually R1 parallel R2 into C. Whatever resistor that you are putting it parallel to this capacitor. So now that actually TP or the tau p will reduce. The tau p will reduce. What do you mean by tau p reduces? The pole further moves away from the imagined axis. Suppose if I take this as 1K, 1K, 1 micro. When it was 1K and 1 micro, where was the pole? The pole was at minus 1000. Minus 1000. Now, where is the pole? The pole is at, so what is this? You have R1 parallel to R2, 1K parallel with 1K will become, okay, this will become 0.5K. So 0.5K into 1 micro will become 0.5 milli. So what is tau p? Tau p is 0.5 milli. So then the zero frequency, the omega p will become minus 2000. Minus 2000. The pole which was there at minus 1000 will go to minus 2000. Minus 2000. So this will actually move from here to here. Why it has moved? Because the time constant is reduced by half. So that's why the frequency which was there at minus 1000, or the pole which was there at minus 1000, has moved to this. How about the 0? Again, you don't have a 0. You can see there is no 0 here. Zero. And of course we have this, okay, the term which was 1 here, now it is replaced by this. So we'll see this later. So since we are worried about the pole 0 position, the pole has moved from minus 1000 to minus 2000. There is no change in 0 position. 0 is there at infinity. Now also 0 is not there at a finite value. It's at a infinite value. Correct? The summary is, if you have this type of circuit, is a transfer function. If you have a resistor in parallel with this, you have this as the transfer function. Suppose if you have a resistor in series with that, in series with this, you will have a transfer function which is totally different, but you will also have a zero. A zero is also coming to picture, which will go be at a finite level, at a finite position. So this is how adding a resistor in series or in parallel is going to totally change the pole zero position of the system. So let us move on to another set of circuits where we have something like this. So let me just start with this. This is a capacitor, this is a resistor. So I'm supposed to find V naught of t here. This is V naught of t. This is I of t. This is I of t. So I'm supposed to find the position of. So let me write its Laplace equivalent. When I write it Laplace equivalent, this will become 1 over SC, and this is R. The current will become IFS. This is V naught of S. This is V naught of S. Ground. What is V naught of S? It is nothing but IFS multiplied by R. But IFS is nothing but the voltage across this capacitor, which is V naught of S minus V naught of S divided by the impedance. Impedance is 1 over SC. So this ultimately becomes V naught of S minus V naught of S into SC. So this is IFS. So can I now replace V naught of S now can be written as V naught of S minus V naught of S into S into C into R. So how do I write this? V naught of S now can be written as 1 plus SRC is equal to V naught of S SRC. So what is V naught of S by V naught of S? It is nothing but SRC by 1 plus SRC. So let me take this as R1, R1, R1. Okay, let me say this as R1, R1. Whatever R is there, let me place it. Suppose if R1 is equal to 1 kilo ohm, if this is equal to 1 microfarad, if you can see where is 0, 0 is at origin. 0 is at origin, whereas pole is at minus 1 over R1C. So pole is at minus R1C. So now, since the values are now given, I can easily locate the poles and zeros in the S plane. So there is a 0 at origin, but there is a pole at minus 1 over tau p, which is nothing but minus of 1 over 1 milli, which is nothing but minus 1000. So there is a pole at minus 1000. There is a 0 at origin. There is a 0 at origin. So quickly, let us put a resistor in series with this. Find the transfer function. Let us put a capacitor. Sorry. Let us put a resistor in parallel with this. Let us find what the transfer function. So this is S7. So what is the modification we have now? We have a modification something like this. So let me have a resistor in series with the capacitor and try to find what is the change. So this is R1, R2, this is V0, this is V of t, this is I of t, this is V naught of t. I can write its equivalent Laplace, which is nothing but R2, and this is 1 over SC, this is R1, this is V naught of S, this is IFS, this is a loop current, this is V naught of S. So what is V naught of S now? V naught of S is IFS multiplied by R1. But what is IFS? It is the potential difference, which is V of S minus V naught of S divided by the resistance, divided by the impedance, which is nothing but R2 plus 1 over SC. Upon simplifying, I can write this LCM, taking LCM, V of S minus V naught of S into SC divided by 1 plus S R2C. This is my IFS. So then what is your V naught of S? V naught of S is equal to V of S minus V naught of S multiplied by S R1C divided by 1 plus S R2C. This is what is V naught of S is. So let us simplify this. So it is V naught of S, cross multiply this will become 1 plus S R2C is equal to V of S minus V naught of S into S R1C. So let me simplify this by taking V naught of S onto one side. This will become S R2 plus R1C is equal to V of S into S R1C. Correct? So now what is V naught of S by V of S? So now this has become S R1C divided by, correct? S R1C divided by 1 plus S R1 plus R2 into C. Okay, the previous case when you had this circuit 1 micron 1K, you had a 0 at origin and there is a pole at minus 1000. Let us see what happens to this. So now the moment you add a resistor here, the 0 position still remains at origin. However, the pole portion, the time constant is actually increased. When the time constant increases, actually the pole frequency will reduce. So in the earlier case, we assumed this as 1 micro and 1 kilo and 1 microfarad, 1 kilo ohm. So if I add 1 kilo ohm in series with this, so where is this? So will it not be S into 1 milli divided by 1 plus S into 2 milli? This will become 2 milli. So what does this S 1 milli will indicate? This will indicate there is a 0 at origin because not 1 plus. So there is a pole at, so there is a 0 at origin. Where is the pole? There is a pole at, so what is this 2 milli? 2 milli will actually 1 over 2 milli will become, so this is tau z is, this is not tau z, okay, tau z is, since it is 0 plus something, the origin or the 0 is at origin. What is tau p? Tau p is actually equal to 2 milli. So what is omega p? It's actually equal to 1 over 2 milli. So 1 over 2 milli is actually 500 hertz. So this is now minus 500 hertz, matlab radian per second. Now this when you suppose if you just compare this with the one, suppose if I add 1 kilo ohm, this remains there at origin, whereas this will move from here to minus 500 if you add another 1K in series with this. So that is the change. The 0 remains at origin, whereas pole moves from minus 1000 to minus 500. It's actually move closer to the 0. Now let us see what happens if I add a resistor in parallel to the capacitor C. So let us see the effect of adding a resistor in parallel to. So what I'll do, I'll have this as my circuit. 1 second. This is my circuit. So this is, I'm adding this capacitor, this resistor in series with capacitor C, and this resistor is as it is R1. This is V naught of T. This is V in of T. This is I of T. So I can write its Laplace. So what is its Laplace? it is 1 over SC, whereas this is R2 only, whereas this is R1, this is V naught of S, this loop current is IFS, this is VFS. Done. Let me write this. But what is IFS? It is nothing but V of S minus V naught of S by the parallel combination. It is 1 over SC parallel with R2. So what is 1 over SC in parallel with R2? It is R2 by 1 over SC plus R2. This will become R2 by 1 plus S R2C. So I can rewrite this as V in of S minus V naught of S multiplied by 1 plus S R2C divided by. So then what is V naught of S? V naught of S is equal to R1 by R2, correct? So it is R1 by R2 V in of S minus V naught of S into plus okay, plus S R2C. So then I can write this as, so V naught of S R2 plus, okay, this R2, and shall I write what is this now? Yes, again S R1 R2C plus R1 is equal to V in of S R1 into 1 plus S R2C, correct? Now be careful here. So I just, this is multiplied and okay, fine, this is what I'm having. So how can I rewrite this? I can rewrite this as, again, while writing the final transfer function, it should be in the time constant form. You cannot simply randomly stop it here. V naught of S, V in of S is equal to R1 into 1 plus S R2C. This is already in the time constant form, whereas this I need to bring it in time constant form. So what do you have? You have R1 plus R2 plus S into R1 R2C. So in the denominator, let me take R1 plus R2 as common factor. Then I'll end up with R1 into 1 plus S R2C. So you take out R1 plus R2 outside the denominator, then this will become 1 plus S R1 R2 by R1 plus R2 into C. So then what is this? This is actually R1 divided by R1 plus R2, correct? Multiplied by 1 plus S R2C divided by 1 plus S R1 parallel R2C. So this is V naught of S by V naught S. See now, uh, is your 0 moved from origin to minus 1 over R2C? Where is the pole? The pole is moved to minus 1 over R1 parallel R2C. So now the poles and zeros have totally moved to different position. If you again take this as 1K, 1 micro, and if you add a resistor 1K in parallel to this, what are the corresponding positions? So the 0 will move to minus 1000. How about pole? Because this is 1 milli, sorry, this is 1K in parallel with 1K and 1 micro, this will become 2 milli. So this will go to minus 2000. The 0 will come out from origin and will be settling at minus 1 over tau, which is nothing but this value. That is, this is your, sorry, this is tau z is actually, tau z is minus, sorry, this is R2C only, it's not minus. But what is your frequency? The pole frequency is at minus 1 over tau p. What is your zero frequency? Zero is at minus 1 over tau z. So tau is actually R into C, sorry for that. So now, where is 0? 0 is at minus 1 over tau z, which is nothing but uh, minus 1 over 1 milli, which is minus 1000, and this is minus 1 over zero point 0.5 milli, which is minus 2000 radian per second. Typically, what we are trying to see is what happens to this circuit having a capacitor and a resistor here. So then this resulted without having anything extra. This is there at origin, this is there at minus 1000. The moment you added a resistor in series with this, so this has moved to, this has actually moved to minus 200, sorry, minus 500. Can you see? Has it moved to minus 500? So this has actually moved to minus 500. That's what we saw. So this is how it has happened. When you added 1k, so the pole actually moved to minus 500. The 0 was still at origin because this is not having 1 plus. But when you add a resistor in parallel with this, in parallel with that, can you see this has resulted in 0 coming out of the origin and then settling at minus 1000, and the pole moves away towards minus 2000. So this entire study indicates that for an electric circuit, if you add a resistor in series or in parallel, the pole positions will totally take a different value, different position depending on the values of the added resistor and the existing RNC values, Okay, we'll see a few other circuits and try to find out a circuit diagram for a given required poles and zero positions. Thank you.